Hi, everybody, and welcome to another edition of the Extreme Performance Series video blogs. Today, I have Qasim joining me from the performance engineering team, one of my performance peers and mentors who's been working in the memory space. And so, first of all, Qasim, why don't you give yourself an introduction? Who are you and what do you do?
Hello, everybody. I'm Qasim Ali, and I'm a senior staff engineer at VMware. I have been working in the vSphere platform performance team for the last 13 years now, and I've worked on a variety of resource management projects. More recently, I've talked about how we have optimized the CPU scheduler for different processors like Intel and AMD. And more recently, I have been focusing my attention and leading the performance efforts around software memory tiering.
Now, that's a pretty kind of cool space here. And so I'm excited to learn a little bit more on what you've been up to there. So I understand you have some information to share with us today. What do you got, Qasim?
In the vSphere team, we have been working to build a prototype for transparent software memory tiering support. What does it mean for the end user? So at a logical level, you would still see your VMs and how you would like to configure them. For example, in this case, this is your familiar screenshot with editing the virtual machine settings. So you would continue allocating your memory just you're used to. For example, you just configure it as VRAM, and underneath the covers at the physical level, you don't need to be aware of what different types of tiers you have. For example, you have tier 1 memory, which could be an expensive DRAM or high bandwidth memory, and tier 2 memories, and which are much cheaper and bigger types of memory, and they are slower as well. For example, Intel Optane, you have CXL DRAM coming up, and then a lot of NVMe devices. So in general, the vSphere will decide what tier to use and when to use it. And the memory available to the host would be the summation of all the tiers available. Now, if you think about it, that is the right approach for software vendors and especially hypervisors like vSphere. Because if you look into the past history, 3 years, folks have changed their operating system, they have changed their applications for a particular type of memory, for example, Optane. Now, whenever a new device comes into the market, for example, CXL comes in or high bandwidth memory comes in, you cannot keep on changing your applications or guest OSs. So it's a natural transition that we at the software level, at the hypervisor layer, have a transparent memory tiering solution. And that's what we are working on, Mark.
Well, and now that's kind of neat, but I know a lot of people will jump up and say, well, if you're doing this all behind the scenes, what does that look like? Prove to me it's going to work.
Just to begin with, this is the CPU memory and storage configuration of a host that I work with. So this is a Dell PowerEdge Intel Cascade Lake with 28 cores per socket. So I have 192 gig of DRAM just as a proof of concept. For the tier 2 memory, I have used 128 gigabyte DIMMs. Now, out of these DIMMs, I have just used 384 gig of tier 2 memory, so which is 2 times more than DRAM. And the storage I have is read-write intensive NVMe SSDs, and of course, this is a prototype in ESX. Now, how does it look like? So if you look at this vCenter screenshot, right, memory shown in the red rectangle, it's showing up to be 1.7 terabyte. So 1.5 terabyte tier 2 memory, 192 gig of DRAM. So 1.5 plus roughly 200 is 1.7. So all of the memory is available for the application, for the VMs. And then we will transparently allocate what we think the workload needs. Because if you think about it, at a hypervisor level, we have much more detailed knowledge about the working set of the workload, about the behavior of the VMs, how many VMs we are running. We can do a better job than perhaps hardware tiering solutions. So this is how it will look like to the end user. Now, let's see what sort of performance we get with certain benchmarks. So to begin with, I'm going to start with a performance of SQL Server using HammerDB. I used a TPC-C profile, which is an OLTP, 70% read and write. And OLTP stands for Online Transaction Processing. So on the x-axis, I have the number of VMs. So this is a scale-out test. On the y-axis, I have normalized the performance with respect to one DRAM system. So DRAM system, again, to recap, is 192 gig, and tier 2 memory to enable software memory tiering, I have 384, which is 2x more. That's the amount I the test is going to use. And again, the number of cores, total cores on the host is 56. If of course hyperthreading is enabled, so you have 112 hyperthreads. So I'm going to show you two lines. The first one is DRAM performance. So as you can see, it scales pretty linearly up to 4 and then starts to taper off even at 6. This tapering off is just a characteristic of the workload. If you have multiple VMs running on a NEMA node, there is hardware level memory contention. So you cannot get away with it, right? So it's just a characteristic of the workload. Now, after 6 VMs, I cannot run this workload anymore, because at 8 VMs, 8 times 32 is 256 gig, which is much more than the DRAM capacity. That's around 192 gig, right? Now, in this case, we go into memory overcommitment zone. If you guys are familiar, in memory overcommitment, we do ballooning, which means taking out memory out of the guest OS. As a result of that, guest OS starts to swap pages, and SQL Server doesn't like that. So the SQL Server transactions would time out. Now comes to the rescue is software memory tearing, and I could scale it up all the way to 12 VMs, and 12 VMs because the math nicely adds out to 12 times 16, which was the active working set of this workload. So 16 gig times 12 is 192 gig. That's getting pretty close to the DRAM capacity. Remember, there is some overhead 10 to 12 gig for the VM kernel. So we are already pretty past the DRAM size in this case. Now, the reason for the tapering off here is there are a couple of reasons. The first one is I have 8 SSDs, right? So after the 8 VMs, I'm using one SSD for multiple VMs. So that's going to hit some of the storage performance. Now, the second one is as I keep on increasing the VMs, some of the working set would fall into the tier 2 memory, which is a slower device. So the device which I'm using has at least 2 to 4x read and random read latencies, and write latencies are even worse. So given that fact, it starts to taper off. And then one of the other reasons is I'm going into the hyperthreading region. So if you, for example, for 8 VMs, 8 times 8 vCPU is 64, which is more than 56 cores. So that's going into the hyperthreading. You guys are aware hyperthreading doesn't give you 2x performance, roughly 25 to 30%. So after 8 VMs, you start to utilize hyperthreading. Now I've put this nice table here just to sort of prove to you guys that we are going into the hyperthreading region. What is the cost of doing software memory tearing? It doesn't come free, right? So if I do the math at 12 VMs, and you can see from the right-hand side table that the system is already maxed out. So the amount of cores the software memory tearing code was taking was about 1.5 cores. So if you divide 1.5 by 56, that's about 2.6% CPU overhead. I would say that's very little cost to pay for such an efficient, transparent memory tearing solution. So the key takeaway from this slide, I know it's a bit busy, is you get 2x more VM density with software memory tearing with increased performance. Now, the next chart, I'm going to show you how much bandwidth is going into different tiers. The first one being DRAM, and the second one, of course, being the slower memory. And the reason I'm showing that is to explain the performance chart in more detail. So in this case, on the x-axis, I have the number of VMs running. And then on the y-axis, I have the bandwidth in gigabytes per second. Now, the first set of charts is the DRAM activity. So you can see at the DRAM read and write, it's almost adding up to 60 gig, which is pretty high for a workload. Now, how much of that bandwidth is going into the other tiers? So if you see these bottom two lines, which is the read and write bandwidth, the read bandwidth, it starts to hit close to 3 gig if you look at the 12 VM data point, and then 1.9 for the write. So this slow increase of the consumption of bandwidth indicates that your active data set is lying in the tier 2. And our algorithm makes sure that most of the data is in DRAM, and that is why you see this nice scaling chart, which I showed here. And it is important to manage these resources efficiently in a tiered system because that's the key to performance. As you can see from these charts, the amount of traffic going to the tier 2 is limited. Now let me jump to the second workload, which is again running SQL Server, but this time with TPC-H profile, which is online analytical processing. In this case, we have used a larger VM size, which is 20 vCPUs, increase the VRAM to 120 and 240 gig, depending upon how much memory we have available. And the virtual users in this case is equal to the number of vCPUs running. For example, we are running a 20 vCPU VM, we would have the number of virtual users to be 20. And the way the performance metric works is all these virtual users are executing a set of 22 queries, the analytical queries. And we choose the user which is the slowest, and we take the geometric mean of those 22 queries. And the end result is the performance metric, which is completion time. And of course, the lower the better, because this is the completion time of the queries. In this case, the active memory is 85% of VRAM size. Now, I say keep on referring to active memory is because it is important to monitor the active memory and know the active memory of your workload. And active memory is, as the name indicates, the amount of memory that is consumed or touched actively. Of course, there is another counter which is called consumed, which means how much memory is being allocated by ESX. So in this case, the active memory, 85% of VRAM size means the VM is pretty active. So whatever is the VRAM size, your working set is close to that. For this experiment, we scaled out to 4 because these were larger VMs. So 4 times 20 is 80 vCPUs on an 80-core system. Now, we could have increased the vCPUs more, but for analytical workloads, increasing the vCPUs does not result in reduction of query times. So it made sense to have vCPUs equal to number of cores. The DRAM is 512, and we use 2x more tier 2 memory, which is 1 terabyte. Now, if you look at the different configs, so we have the same set of 4 VMs, 20 vCPUs. We are not going to change that. The only change we're going to do is the amount of VRAM. Now, the first DRAM system config is sort of our baseline, right? And the next row, the second row, which is the exact same config, but we ran it on a tiered system. And by tiered system means that has the 512 gig DRAM, just as the DRAM system, but it has additional 1 terabyte of tier 2 memory in it. Now, given the definition and the characteristics of the working set, right, 85% active, one would easily guess that, okay, so the working set is fitting in DRAM, the performance should be all clean. So the results showing 110 seconds, 110.9 seconds compared to 110.5 in DRAM is sort of a proof point that the system works as designed. Now, the system works even better when you're trying to overcommit memory with respect to DRAM. So in the third row, you can see that we have allocated 240 gigabyte per VM. Now that multiplied by 4 is roughly 1 terabyte. So we are way above DRAM. Now, the general guideline in a memory tiered solution is don't let your working set past the fastest tier. In this case, we are sort of pushing the envelope. So your mileage may vary, but from our results, we saw a 30% reduction in query times, because in this case, the SQL Server was able to use more buffer cache, and that resulted in lower query completion times. So the key takeaway is using of tier 2 memory in an efficient manner, and vSphere does that behind your back, completely transparent. You can use that memory in a cost-effective way and get better performance.
So I think that's pretty neat. I mean, so basically kind of what you've demonstrated here is that by design, it's working the same as it would with just one single tier of memory. But now that we have this ability to use multiple tiers, and the applications may be able to take advantage of things like buffer cache, right? Now we can use multiple tiers, we can increase performance at, an economical set of costs, again, completely transparent. I think that's, that's an amazing technology to underpin everything here.
Just to finish off what you just said and to add on to it, we know that the data sets are increasing, right? So we do need larger memory, but not at the DRAM cost. We want them cheaper. We want the memory bigger. We want disaggregation. We want pooling of memory. We want to be able to add memory without going through all the cycle of optimizing the application first for a specific kind of memory. So in this software tiering solution, at least our results at this point shows that we are ready for the next big memory revolution. Whatever is the next sort of devices coming out, for example, it seems like CXL is the way forward these days. We are ready for technologies like CXL.
Well, that's awesome. Thank you, Qasim, for joining us today, and look forward to speaking with you again in the future.
Okay. Thank you, Mark.
Well, thanks everybody for joining. We'll see you soon on the next edition of the Extreme Performance Series video blogs.